Hello, fellow Pyninsulators. I'm Colin, and tonight we are going to cover how not to crash your program by hitting the max number of open files. I'm sure every one of you has run into this problem at one point or another. My first time was when I wrote this seemingly innocuous program. I define a list, print some numbers, print the length. Yeah, there's no way that's going to work, but let's give it a go. Yep, there it is. Oh, I just noticed I screwed up the formatting. This should be down here. There we go. So I'm sure you can see why that happened. And I'm sure the same thing has happened for everyone here. You saw that error no too many files message for the first time, and you realized what you were doing wrong, and so you searched the internet for how do I raise the max file limit, and all the answers were for Linux, but you're using Windows. That's rough. Luckily, there's an easy cross-platform solution to this issue, and that is, don't open thousands of files at the same time. Okay, those last 15 sentences were a bit of an exaggeration. Most of you have probably not run into this issue in practice. But it can happen accidentally, and because of this, we've all been taught that the correct way to open files is like this. So what's going on here? Well, there's this with thing, and there's some code indented beneath it. Well, what this does is guarantee that the file gets closed after the indented code finishes running, and we don't have to remember to do it. By the way, this is the actual file name of this script, and you can tell I'm not on Windows because double quote isn't a valid character in Windows file names. Okay, so what does that with thing really do? Why is it the correct way to open a file? And why does nobody actually run into the open file limit in practice, even if they don't use with? Let's tackle those questions in reverse order. Consider this program. Will this work? Or will it hit the limit of open files? Raise your hand if you think it works. Good, I see several hands. This program does work, and the reason it works is garbage collection. I won't go into the details today, but all you need to know is that Python keeps track of how many references exist to every object. If an object is assigned to a name, that's a reference. If an object is put in a list, that's a reference. A reference is just anything you can use to refer to the object. If all of the references are gone, then you no longer have any way to get to the object, so Python's garbage collector cleans it up. In this program, the name f is a local variable in the readData function. It's the only reference to the file object returned by open. So when the function returns, no reference to the file object remains, and it gets cleaned up by the garbage collector. And when I say gets cleaned up, I mean that the object's dunderdel method is called. Anybody want to guess what a file object's dunderdel method does? We can easily find out. We'll just create a file object and call dunderdel, and then have no idea what happened. Let's start over. And this time, let's grab a copy of all of the file object's attributes and their values. Then we'll call dunderdel. And then we'll grab another copy of the file object's attributes and values, then iterate through those and take only the ones where the after value is different from the before value, and print that. Great, so it turns out that the file object's dunderdel method just closes the file object. So this all explains why this program doesn't run into the open file limit, while that program does. This one doesn't keep references to the file objects, so they get closed by the garbage collector. And this is why most people don't run into the open file limit in practice, even if they don't use with. As long as they don't accidentally keep references to their file objects, the garbage collector takes care of closing the files. So why do we need with at all? Well, it makes it practically impossible to do the wrong thing. And impossible to do the wrong thing is much better than unlikely to do the wrong thing. It's also less code, and there are a bunch of other useful things the with block can do. But before we start looking at examples, we need to know about what context managers really are. Context managers and with blocks go hand in hand. So, what is a context manager? Well, this is an easy question to answer for yourself. Just go to your web browser, type docs.python.org/3/glossary.html entirely from memory, Control F for context manager, and you'll find this definition. An object which controls the environment seen in a with statement by defining dunderEnter and dunderExit methods. See PEP 343. That definition is technically correct. If an object implements the dunderEnter and dunderExit methods, then by definition, it is a context manager. That's still not very useful unless you know when and how these methods are called. Also, speaking of calling methods, it's a pain to keep saying dunderEnter and dunderExit. So for the rest of the talk, I'm just going to call them enter and exit, and you'll know what I'm talking about. Let's follow this link to the documentation of the with statement. The part we're interested in is this description of how the with statement is executed. I'll summarize. First, the expression following the with keyword is evaluated, which produces an object. Next, that object's enter and exit methods are loaded for later use. This is done so that we know up front whether the object is really a context manager. If either of the methods is missing, an error will be thrown at this point. Next, the enter method is invoked. If there was a target, that's the word after as, the return value is assigned to it. Next, the suite is executed. That's the indented block of code that we think of as inside the with. Finally, the exit method is invoked, possibly with exception information passed to it if the suite threw an exception. Also, if the suite threw an exception, then the return value of the exit method determines whether the exception is suppressed. That was fairly technical, but it all boils down to this. The with statement lets you put a context manager here and some code here, and the context manager's enter and exit methods will be automatically called here and here. This means you can do some setup and some teardown with only a single line of code, and there's no way for you to forget to do the teardown. It lets you write this instead of this. Now let's look at some other examples. Here we're running the help function, which prints text to standard out. But in this case, we don't want the text to go to standard out. Instead, we want to capture the text so we can do something else with it. So we temporarily replace sys.standardout with a string IO object. But we do it politely by saving the old value and restoring it when we're done. With a context manager, that can be rewritten like this. And this context manager already exists in the standard library, in the context_lib module. Here's another example. We're acquiring a lock, doing some stuff, and releasing the lock. Here we're doing the same thing, but better. Earlier, I explained context managers as encapsulations of cleanup and teardown operations, and that is how they're used most of the time. But I like to think about context managers in an even more general way. Everyone knows that functions let you factor out a block of code, giving it a descriptive name and letting you use it in multiple places. You can think of context managers as the cooler, older siblings of functions. Instead of one block of code, context managers let you factor out 2 blocks of code. But it's not just any 2 blocks of code. They need to be related, and they need to surround some other code. So I like to think of context managers as a way to factor out code that surrounds other code. Context managers are also useful for a bunch of other things, like database connections, database transactions, patching things in unit tests, timing how long some code takes, and even running async tasks concurrently in a clean way. So now that we've seen some of the ways they can be useful, let's talk about how to write our own context managers. There are 2 ways to go about it. The first is to define a class with enter and exit methods. But I'm not even going to show an example of doing it that way, because the second way is much better. Here's the second way. Simply import the context manager decorator from context_lib and write a regular old function. Well, regular except that it uses yield, so it's actually a generator function. The context manager decorator is able to take this generator function and turn it into a full context manager. The enter method is everything before the yield, and the exit method is everything after the yield. The yield itself represents where the code placed inside the with block will run. Right now, this context manager doesn't have any special exception handling, so if the code inside the with block throws an exception, we won't see the time get printed. If we want to fix that, we just need to remember that the yield is a stand-in for all the code in the with block. So we can just add a try finally around it, and that takes care of it. Oh, also, if the function yields a value, that value is what gets assigned to the target name here. I'll wrap up by touching on 2 important aspects of context managers that can cause some confusion. The first is a question of broad scope, and the question is, scope? New Python programmers sometimes assume that the with block defines a new scope, and so f is only defined here. But f is actually defined here. In Python, the only things that define scopes are modules, class definitions, and function definitions. With blocks don't change anything. All these variables are available in the whole function. This is important because it allows us to do some neat things with the object returned by the context manager. Here, the context manager returns a result object, which isn't meant to be used until after the with block. At that point, the object can be used to retrieve the elapsed time in seconds. The last topic we need to touch on is global state. Sometimes you need to use a context manager to modify a piece of global state. We already saw one example of this, the redirect standard out context manager. It works by temporarily modifying sys.standardout, which is a global variable. Now let's imagine what might happen if we tried to use this in a multi-threaded program. If thread A were in the middle of this long operation and thread B tried to print something to standard out, thread B would see the modified sys.standardout and end up printing to the log file. But there's nothing we can do to fix it because sys.standardout is a global and we can't change that. The same issue could occur in an async program. Just replace the word thread with coroutine. So we can't fix sys.standardout being a global, but we can avoid this type of problem in our own code. Here's an example from a project I worked on recently. Log prefix is a context manager that causes every log message to be prefixed with the given string. The output looks something like this. You can see that each line logged by the code inside the with block has the prefix added to it. This is a perfect use for a context manager. It encapsulates a somewhat complex operation behind a very simple, easy to understand interface. Let's go behind the scenes on this one and see how it works. We have a global variable that holds the current prefix and a filter function that just attaches the current prefix to each log record. We call basic config to configure the log level and format, then attach our filter function to the handler that basic config created. All the context manager actually does is set and reset the current log prefix variable. It also takes care of appending the given string to any existing prefix so that uses of this context manager can be nested. Now let's address the global elephant in the room. Using a global like this is not safe in a multi-threaded program because the prefix set in one thread can affect log messages being logged from another thread. But unlike the earlier example, we created the global variable in this case. So we can solve this problem easily by replacing the global variable with a thread local variable. This means that each thread has an independent current log prefix, which solves the problem for multi-threaded programs. Async programs running in a single thread still have a problem. Luckily, since Python 3.7, we have a very similar solution that solves the async case too. It uses a context var, which is a new concept that was introduced to solve exactly this problem. You can think of it like an upgraded version of threading.local that also supports async programs. The way it works is that behind the scenes, async IO manages the contexts and always keeps the current context available in a thread local variable. This only works because async IO is fully cooperative. If you use a different async framework, it might not have this integration with context vars yet. And with that, let's move on to talking about. If you're seeing this message, that means that my talk was interrupted due to a timeout. Luckily, thanks to context managers, I was able to leave this emergency message to let you know that everything is okay. Hopefully I got through enough of the material that you'll be able to start using context managers in your own code. They're really great. Bye!